So hi everyone, and welcome to CERIAS security seminar. And today, we have our speaker is Adil Ahmad. Adil Ahmad is the second year PhD student at Purdue, and he's working on system security. And today he's gonna present his work on how we use the Oblivious Ram to implement the file system, especially for the Intel SGX. So let me pass it to Adil to present the paper.
Okay, thank you. Hi everyone, as just said, my name is Adil Ahmed. I'm a second year PhD student being advised by Professor Byung-Young Lee. So my whole area of research is system security, and my recent focus has been a lot on trusted hardware, especially side channel mitigation within trusted hardware. So I'm going to be presenting our paper, Obliviate, a data oblivious file system for Intel SGX, which is due to appear in NDSS during the next week. So it's me along with my with other members of my group from Purdue University who have authored this paper. So let's begin. So, well, cloud computing. With the advent of cloud computing, there's been a lot of good things about cloud computing. There's been a lot of threats and security issues about cloud computing. So for example, let's build on a very simple scenario. Let's say that there's a user who wants to store, let's say, some sort of trusted data, some sort of sensitive data on clouds. Now the problem is that public clouds, you can name any, they're not completely trusted, right? So the cloud provider has access to the machines that it rents out to you. And then there are other tenants that are also sharing machines with you within the clouds. So that means that there are a number of ways that other people, the cloud provider, or other tenants can sort of look into what you're doing and sort of leak out your sensitive information or whatever sensitive data that you've stored within the clouds. So let's look at this scenario. Now you have the untrusted cloud provider, the untrusted tenants. So, well, that's why trusted hardware was sort of imagined, right? Because the user is going to say, okay, let me use a trusted hardware, and therefore, using the trusted hardware, I can sort of say that this is secure, sort of say that whatever code or data I'm running within the trusted cloud is secure. And one such trusted hardware is Intel SGX, which has been recently commoditized. Not recently, it's been almost 2 years. So it's been commoditized by Intel with the Skylake architecture. So what a normal user is going to perceive with Intel SGX and other trusted hardware is that there is a trusted region within the clouds that is completely impenetrable by the cloud provider, by other tenants, by any sort of higher privilege or same privilege components. So that is what a normal user is going to perceive of Intel SGX and other trusted hardware. And it's going to say, okay, thanks a lot SGX, that, you know, thanks a lot trusted hardware, everything is secure, I'm going to live my life happily. But bear with me when I say this, that the real world is a bit more complicated than that. So to understand the complications that arise with trusted hardware such as Intel SGX, you have to understand how Intel SGX works, what is Intel SGX. So Intel SGX, so let's consider that when a computer boots up, you have your physical memory. What the processor does with the physical memory is that it creates a very small region inside the physical memory, which is called the EPC, which is the enclave page cache, which is reserved during boot up. So it is always randomized during boot up. So it's not going to be the same space, but in your physical memory or your DRAM, to be more particular, there's going to be a very small space that's going to be reserved by the processor. And the processor is not going to allow any access onto this small memory region apart from in a trusted state, which we call the enclave state. So, and this trusted memory region is just 128 megabytes. And that's obviously for performance reasons. You don't want your whole DRAM to be trusted because of ensuing properties. So let's suppose, so what happens when, so what do we say, what is an SGX? What is an SGX program? How is it different from regular programs? So the thing is, well, a regular program has its address space, and you know they have their different components, the stack, heap, etc., etc. So you can imagine that within a regular program's address space, you just sort of create another address space. It is exactly the same as a regular program. It also has its code, stack, heap, etc. regions, but it is trusted. Now, it is a trusted region, and all the memory pages allocated to this trusted region are only from within the EPC. So normally, let's suppose in a normal program, you can technically, the operating system can technically allocate any page whatsoever from wherever in the physical memory. But these enclave pages will always remain within the EPC. So, and the EPC is a trusted region where which the processor controls. So that is where the whole notion of security comes from. So what would happen is that there are system components, even higher privileged system components like the operating system or the BIOS or VMM, etc., hypervisors, etc. What's going to happen is these system components, even if they try to access this certain memory region, let's say the EPC memory region, the processor is just not going to allow it. So it's going to be access restricted by the SGX processor. So in that sense, you've technically created a very secure space within your program's address space where you can execute code, where you can store your data and do whatever you want, and sort of think that everything is happening very smoothly and very securely. So this is a very brief overview of how Intel SGX works and how Intel SGX programs operate. So let's move ahead. So now let's talk about the file system. Now, like SGX programs, like any regular programs, have to access file system, have to access files, certain files, etc. So for example, let's take 3 programs. Let's take a database program, a web server, and a personal storage program like Dropbox. And we say that this program has to access, everything is stored in the form of files. So we have to access files to write data, to read data, to read a query, insert a query, select a query, etc., etc. So, but now you can see that these are sort of enclave protected applications. Now they're going to try to access the disk to access a file. What's going to happen is enclave programs, like all regular programs, are ring 3. So ring 3 programs in the current operating system models cannot access the disk on their own. That is why the operating system comes into play. So you have to rely on the operating system, which is a ring 0 system, to actually access the disk like a regular program. So, well, that creates a complication, right? Because in the threat model of SGX, the operating system is technically controlled by the adversary, i.e. the cloud provider. So that means that if you're relying on a system that is controlled by an adversary for a certain let's say application, like to access files, for example, in this scenario, that means that definitely there is something that would be a problem. So for example, the operating system, which could potentially be adversarial, what the operating system could do is it could simply log whatever system calls you make. Like for example, it could log that you ask to open this file, and then you ask to read a certain offset, because all the system calls are definitely going to be handled by the operating system. There is nothing preventing the operating system from knowing what exactly you're doing with which file, and etc., etc. What you're doing, are you reading, are you writing, etc. So this is a problem. Well, SGX has been there for almost 2 years, so this is not a new problem. People already know about this problem. So what happens is that a lot of people in academic research, they propose a new file system which they call the in-memory file system. So the in-memory file system is very similar. What would happen is, instead of reading from the operating system during program initialization, what the process is going to do is that it is going to preload all the required files into the enclave and save it within the enclave memory space. So that means that, for example, if you have to access a.txt and b.txt, what you're going to do is you're going to just read the whole files into memory before program execution, and you're just going to read everything, read and write using inside in memory. And then when you're done, when the program terminates, you're just going to dump everything back to the disk, again using system calls and the operating system. But then the operating system technically doesn't really know what you've done within the execution frame. because everything was executed within the trusted enclave. So this is one of the proposed solutions to this problem. However, the problem comes about when you go into detail about SGX and you understand that SGX is not a completely trusted environment. If SGX had no side channel or had no other sort of attack possible on it, then this would be a very good solution. Yes, but since there are side channels, we also have to consider side channels in this scenario. So this work has been proposed by a bunch of OSDI papers over the course of 2 years. So let's dive deep. Let's dive into the side channel attacks against SGX. So there's an attack called the controlled channel attack. So to understand this attack, consider that in modern operating systems there is a concept of paging and there is a concept of page tables. The page tables are accessible both to the processor and to the operating system. So what would happen is that, let's suppose you have this trusted file system library, which is part of the in-memory file system that we just saw in the previous slides. What would happen is that, let's say the enclave is trying to access certain blocks within this file, within this memory region. And then implicitly, the processor is going to set the access bit because that's what the processor does, and it's required for a lot of optimizations. So in the page table, it is going to set the access bit on that specific frame. And it's going to say, okay, this frame was accessed by this enclave process. So what would happen is it is set by the processor, but again, the operating system, being all-powerful, can actually view the page table. So it knows exactly what pages were accessed. So of course, the granularity of pages is 4 kilobytes, but sort of what would happen is you can still, the enclave would still sort of leak information as to exactly what part of the file was accessed. Let's suppose that this file starts from here. Then you can still figure out, okay, what offset or what granular, in some sort of granularity, what offset of the file was accessed. So this is a control channel attack. There have been 2 different papers that have talked about these attacks and have even talked about improved versions of these attacks. One interesting thing to know about this attack is that this is extremely noise-free channel. This is not like other attacks. This is something that the operating system can view, can technically view every page that was accessed by the enclave, sort of revealing that information outside the enclave and to the operating system. So this is the control channel attack. Let's move on. The second very important attack is the cache attack. The cache attack is not really a new attack. It's always been there for almost more than 15 years now, I guess. So what happens in the cache attack is, like, the cache architecture, as you guys would definitely be familiar, is that all processes, enclave or non-enclave, SGX or non-SGX programs, they all share the cache architecture. So for example, there is one attack that is called the prime plus probe attack, where the attacker simply fills different cache sets with its own data, which is called the prime phase, and then it lets the victim process, which is in our case the enclave, execute. And what would happen is, when the enclave would access certain data, then it would evict the attacker's cache sets and it would fill them with its own data. So the next time around, when the attacker is going to try to access its own data again, so if the data had been evicted in the last cycle, it's going to take it's going to take a much longer time to actually access that data, other than the case that when it wasn't actually accessed. So based on this information, and this is a very possible attack that people have shown is extremely possible, because there is a huge difference between the probe times of an evicted data and a non-evicted data, and which you can measure using RDTSC or whatever clock cycle measuring or performance measuring counters. So this is traditionally called the prime plus probe attack. This is not a SGX specific attack. This has been around for almost 5-6 years, but very recently there have been 3 very good papers who've actually shown that these attacks are even more potent in the SGX environment, because now the operating system is untrusted and the operating system can do a lot of tricks to ensure that there is very little noise for this attack. So let's move on. So now I've just talked about some two very important attacks. Now I'm going to try to describe how these attacks can be carried out in principle. How, for example, to illustrate our point, what we did was we did a case study on Lite, which, as you all know, is a lightweight database program. So let's suppose that in this scenario, there is a doctor or an insurance provider who is trying to access a patient's history. Now, the patient's history is stored on a database in the cloud, but the cloud provider says that, okay, you can have an SGX protected database. Now, there are actually cloud providers who are actually giving SGX enclaves to their clients. So in this scenario, what happens is that the database is technically SGX protected, but the doctor is going to run a bunch of different queries and try to see, okay, what happens. So let's suppose that this database has, let's say, just the name and 2 columns there. That's for the heart condition and the lungs condition or something. And the doctor is going to run different queries on trying to find, okay, for example, what is this guy's heart condition, what is this guy's lungs history, etc., etc., to sort of do a proper diagnosis. So this is so for example, in our test database, what happens is that in the first query, let's suppose that the doctor asks for Bob's heart history. Then in that scenario, what SQLite is going to do is it's going to go into the row that corresponds to Bob and going to access its heart history and going to return that data to the doctor. So let's suppose that we do a Syscall based attack, which is for the native file system. So in this scenario, you can see that the attacker already knows that, okay, this enclave tried to access this database, which is med.db, and tried to read these three offsets. Now the first two, the line 2 and 3 simply correspond to metadata that is always accessed whenever a SQLite database starts. So the first and the last one corresponds to the offset of the row. So that simply says that if we exclude the first two, then we simply just access the seventh row within this database, because each row here is because each row is 8 kilobytes. Sorry, the third entry. So similarly, using the page table attack, you can similarly get very similar traces. So the attacker definitely sees that, okay, the first two are very close to each other, are right only 4 kilobyte at only 4 kilobyte offsets, and the next one has a specific X offset. And based on these traces, the attacker can know, okay, based on multiple runs, what the attacker would find out, okay, this is where the database starts from, and at this offset was the access perpetrated. So that means that this entry was accessed. And since again, if let's say the doctor runs the query again a second time, it's going to still be the same. It's still going to give the same memory traces, because of course that's how a file is read. There is no randomization or anything. So the next time around, even on the second run, it's going to be the same query. It's going to be the same memory traces. Then suppose that there is a second query that would happen where what would happen is, let's say the doctor asks for Alice's lungs history. So now the lungs history is technically the third column. So SQLite always goes column by column until it finds the required column. So that's how SQLite operates. So based on this, what would happen is, again, the first two reads correspond to reading the metadata, which is the first and second page of the file. And the next two correspond to whatever you want to access. So it is 40960 here and the next page here. And again, using page table based attacks, you get the same memory traces, you get the same addresses, and based on multiple runs, you can figure out exactly. You don't really know what the query means. Of course, because we assume that this is an SGX protected in-memory file system, but you still know that, okay, for example, this guy was trying to access this entry, and this entry corresponds to this IP address, which can still be used to correlate to sort of leak out some information, which is not really ideal in our scenario. So this is sort of a very simplistic attack. And of course, there are limitations to this attack because number one, the page table attack is just 4 kilobytes in granularity. So that means that whatever you learn would be, if your queries are smaller than 4 kilobytes, then you would still have more noise. Then you would not really know exactly which query it is. But again, this is just to illustrate a point using our test database. So the question comes that, okay, we understand that there are side channels. The side channels are not really new. The first paper, again, that proposed the control channel attacks was presented in 2014, in the 2014 Oakland. So the question arises that what exactly is the way of mitigating this threat? So number one, what we've seen recently in research, in conferences, is that there's been a very particular focus on mitigating individual side channels, individual memory-based side channels, which I believe is a risky approach, because there are always going to be more side channels, and the way trusted hardware such as SGX is created, it has to share some information with untrusted subsystems for performance reasons, for a lot of other reasons, for a lot of architectural reasons, and historical reasons also. So that means that if you're trying to fix individual side channels, or you're trying to mask side channels, especially memory-based side channels, it might not be such a good idea to do that, because there are always going to be more than one side channels, and you can't always fix all of them together. So if you focus on one of them and try to fix them by masking them, by ensuring that, let's say, you don't get the side channels outside the enclave, it's not really a very good idea. I believe so. So the thing is, you have to realize is that memory-based side channels, all memory-based side channels, they rely on predictable access patterns. So the pattern of access has to be predictable, so that, in multiple runs, the attacker can correlate, okay, what exactly are you trying to access? For example, let's say you might want to access a cryptographic key or something. So it does rely on predictable access patterns, and without predictable access patterns, it would be hard for memory-based side channels to be exploited. Then the question comes, how do you provide generic and theoretically sound protections against predictable access pattern-based attacks? So we move on to a concept known as Oblivious Ram, which is a very famous cryptographic primitive that has been around for almost 20 years now. So Oblivious Ram is, just to understand the threat model of Oblivious Ram, you have to understand a client-server model, where in the server, which is an untrusted cloud, what the client is trying to store is, let's say, some sort of data that the client is trying to store within the server, and the client wants to access that data in a secure manner. So by secure manner, what that means is that when I'm trying to access, let's say, block A, the cloud provider or whatever tenant should not really be able to know exactly which data block was accessed. So the user's goal is security, but the attacker's goal might be a potentially adversarial cloud. So it wants to figure out exactly what you're trying to access. So this is the model of Oblivious Ram. So Path ORAM is an improved version of Oblivious Ram that was proposed in 2012 by Emil Stefanov, who was a Purdue graduate. So it's an improved version of Oblivious Ram that uses a tree-based ORAM scheme. So in this scenario over here at the server end, you have all your blocks, all your users' blocks, which are shown by the real blocks in the orange ones. So you have different blocks over here, but then you also have dummy blocks, and you sort of have a tree formation where the number of real blocks in the tree is equal to the leaf of the tree, as you can observe. So that's sort of a construction of the Oblivious Ram tree within the server. And then on the client side, you have a position map and you have a stash. What the position map does is that it simply holds whatever is the position of individual blocks of the client. So for example, A, it says, is stored at 0, 0. So that means to access A, you have to go through 0 and 0 to get A. So whatever the path is, it's stored over here. For B, again, 0, 1. So it doesn't really say exactly where it's stored. It just says that this is the leaf, and you just have to access the whole path. So this stash is just a very small, not a moderately small memory region where you're just going to store the blocks that you're going to access from the server. So let's have a look at how PathOram actually works. So let's say your goal is to access block A. So what would happen in this scenario is that first you would have, the first phase is reading the block. So first, number one, you're going to consult the position map to find out exactly where A is. You consult the position map, it says it's at 0, 0. It says it's at leaf 0, 0. So now what you're going to do is you're going to obtain the whole path 0, 0 and then save it in the stash, which is again your trusted memory region. Now, one thing to note here is that we've discarded the dummy blocks because we don't need those blocks. Those dummy blocks were just to fool the attacker. Sorry, one thing I forgot to mention is that the Oram server is completely encrypted. So the attacker does not know which block is real, which block is dummy. This is a knowledge that is only available to us. It's not available to the attacker because everything is encrypted. So we discarded the dummy blocks and we only stored the real block over here. We do whatever operation we want to do with the block. So why is this secure? The only reason this is secure is because you extracted multiple blocks when you only needed one of those blocks. You extracted multiple blocks, you extracted the whole path, and since the attacker doesn't really know which block is the real or which one is the dummy, the attacker doesn't know which block did you actually want to access. So multiple blocks extracted actually hide the required block, whatever block was required. So let's move on. Now this is secure. Now we can, I hope you guys can all see that this is somehow secure because now you've extracted multiple blocks. But the problem is if we keep with this and we do this again the next time, then we would still leak the same information, right? If we again, to obtain block A, we read paths 0 and 0, then there is no security because then again, the attacker would know, okay, this is the same path that was accessed before, so it must be the same block. I don't know what block it is, but it must be the same block. So that would then defeat our purpose of actually having all this complex structure. So now what is our goal? Our goal is to write back the block in a random fashion to ensure that the next time we read it, the attacker can still not correlate what block it was. So we're going to randomize the position of the block that we just extracted. A was 0, 0 before. Now it's changed to 1, 0. And so this is just random, any random position. It could be any leaf position here. And then we're going to get it from the stash and write it back in the tree according to the new position. So since the new position was 1, 0, the only place in the Oram tree that this block could go was the root node, because that is the only one that is within the path of 1, 0. Again, the important thing is we wrote back to the exact same path that we read from. So we read from here, and we're writing back again on the same path. We can't really write back to a random path because that would again leak some information. We write back to the same path, but we ensure that we write it back to the position. Again, this is the root node here, to the position where it should be according to whatever randomized position we got, 1, 0. So then we write back the block at random position to technically randomize next access. So the next time we're going to access A, let's suppose we have to access A again, what would happen is we would simply be reading the path 1, 0 and not 0, 0 again. So now the attacker doesn't know that whether this 1, 0 corresponds to another block or this block or whatever. So the attacker doesn't learn any interesting information out of this, out of our access step. And the next time, again, it is random, so it is again secure. There is a whole description of why this is secure in the PathOram paper if you guys are interested. So now we're going to go into what my talk is about and what after building this background, I'm going to now discuss what Obliviate is. So Obliviate is technically a memory charm in the Harry Potter series that allows you to the wizard to sort of make the other person forget what happened. So I know this is the usage of this term in this paper is very loose, because yeah, the nerds are going to say that this is not technically the right usage, but I really like the incantation and I won't apologize for that. So if you guys remember this scene from Harry Potter, I'm hoping everyone has seen Harry Potter. Otherwise, you should definitely go see it right now. So what would happen is that Hermione is trying to use that incantation on her parents, so that her parents forget about her, and Lord Voldemort cannot technically mess with them, and they move to Australia or someplace free from, or Canada or whatever, someplace free from Lord Voldemort's influence, somewhere away from London. So in our scenario, what we're trying to say is that Hermione again is going to say Obliviate or whatever. We're saying Obliviate, and we want the operating system, which is exploiting all these side channels, to sort of technically start crying and not be very happy with his or her life anymore, the attacker. So Obliviate is technically a memory charm against the operating system. And in this scenario, let me walk through exactly what Obliviate would do and how it would secure everything. So this is sort of a walkthrough slide. So in this scenario, the program, again, you have any specific program. You can think of SQLite, LiteDBD, whatever, web servers, etc. So there is a trusted proxy. We install a trusted proxy inside the enclave program, which is going to intercept the system calls provided by the program, and it's going to encrypt them and send them to Obliviate. It's going to send them to Obliviate. Obliviate is another enclave. So these are two separate enclaves here. And Obliviate is responsible for handling all file system operations. What this application is going to do is that it is just going to take the messages, encrypt the message. By the messages, I mean the system calls, whatever system calls it wants, and it's going to send them to Obliviate using encrypted inter-process communication. So again, after it sends it there in the Obliviate, which is again an enclave, we have a trusted service which is going to sort of bridge the gap between file system operations and ORAM. Now, ORAM, as we just saw, was very simplistic in its model, whereas file system has a few complex operations that you have to do. So to bridge the gap, we have a trusted service that runs within the enclave, and then we provision it further to actually make sure that it doesn't leak information. We sort of use data oblivious metadata handling, by which we ensure that side channels do not actually leak information from our implementation. And then we access the ORAM server to get the blocks in an ORAM fashion. So at the end, what you're doing is you're actually accessing multiple blocks using the ORAM operations instead of accessing one. So again, this ORAM tree has been filled with whatever files you're going to need. So it is technically an in-memory file system, but different in this aspect that we're sort of going to ensure that each operation is done using ORAM access, so that it is technically oblivious to the underlying operating system. So first point of Obliviate, the first point of this file system is that as all legacy file systems in Linux and Windows, etc., we're going to decouple the file system support from the enclave application. We don't want the application to be handling the files on its own, because again, the whole point of having this sort of a system, having operating system and the operating system handling all this file system calls for you, is so that the program developer, doesn't really have to bother about all this stuff. And we're trying to follow the same model, and we say that, okay, we have a bunch of different enclave applications over here. So all these enclave applications are going to connect to one single central point. This central point, they're going to, obviously we have to ensure this is a secure communication, which can be ensured between enclaves using Diffie-Hellman. And then we have to make sure that Obliviate, this central point, definitely handles all the file system operations, all the file system calls in a secure manner. So that we ensure that this is one central point, and we put all the burden of creating completely secure file systems on this enclave over here, rather than individual enclaves having to do all this on their own. So separation of functions facilitates app development, obviously, so that the developer doesn't have to worry about all this stuff. We handle it for them. How do we do it? I'm going to explain now. So another very important thing is there's supposed to be legacy application support. So now we can't really expect the application developer, and because there are so many applications that are already being developed and can simply be ported within SGX, we don't want all those applications to technically have to change their whole source code to actually be able to support Obliviate or the file or a secure file system. So we're going to install a trusted proxy within the enclave program, which is a very small library of a couple of hundred lines of code. That would just, what it simply does, it is going to intercept whatever system call, especially file system related system calls. It's going to intercept those system calls and encrypt those requests in fixed size messages and going to send them through to Obliviate. Now we use a term here called exitless message queue interfaces, which is sort of that. So the enclave, so to understand this, you have to understand that the enclave can technically access the untrusted part, but the untrusted part cannot access the enclave. So since there is a one-way traffic, we ensure that the enclave doesn't exactly exit. The enclave is still running in the background, but we just make sure that we pass the messages through a message queue onto the untrusted part, which is going to use shared memory interface already implemented within modern operating systems to send all the data through to the Obliviate enclave, which is going to handle all file system operations for you. So again, the second point is there should not be any changes from the application developer at all. So the third part is how do you secure file systems? Now, so when you think about file systems, there are two major things that you have to protect. Number one, you have to protect what file was accessed if you want to create a secure file system. And number two, you have to protect what offset within that file was actually accessed. If you leak any of these two informations, then technically your file system is not secure. Then you are leaking some information. And different applications have different requirements. For example, you can think of a web server. A web server, it's very important. A web server, we all know, is going to read the application completely. So it is much more important that you're able to secure which file was accessed, which HTML file, JavaScript, etc. was accessed, rather than what offset was accessed, because of course the whole file is going to be read for web servers in most scenarios. So on the other hand, we just saw an example of the SQLite database where we showed that the offset information is very important, and we cannot leak the offset information either. So what would happen is, so each file is an ORAM tree. So each file is broken down into a smaller an ORAM tree. If, for example, like let's say this file has 4 blocks, we break it down into 4 different blocks and create an ORAM tree out of it. And then this single ORAM tree is going to protect file offset, because again, whenever you're going to access a specific offset, we're going to ensure that you do one ORAM operation, an ORAM access. And then we have a hierarchical ORAM tree layout where each individual file is again an ORAM tree. So again, using the single ORAM tree, you can protect the file offset. Using the second tier ORAM tree, you can protect what file exactly was accessed, because then you can do another ORAM operation on the larger tree to protect what file was accessed. So at the end of the day, what we ensure is that we're going to protect both the file and the file offset as a result of this. So perhaps the most important part is how do you secure ORAM? Because if you remember ORAM, in the trusted memory region, there was the position map and the stash. And the position map and the stash in the traditional ORAM, it is considered that both of these are in completely trusted memory regions where the attacker does not really know anything about what is happening. Then we can, in those scenarios, then it makes sense to just naively read everything. But in scenarios for SGX already has so many side channels. You can't really expect to insecurely read the stash or the position map and expect that it would be secure. So for example, let's suppose the stash, you have to load from the stash and you have to send it to, let's say, whoever asked for this block. Then that means you have to go through the stash and you have to send you have to copy it from one memory location to another memory location. So you have to load it from here. But then again, side channels in SGX are going to be a hassle, because now again, using the side channels, the attacker knows exactly which offset within the stash was accessed and which offset has been copied from this memory location to whatever final destination location. So this would again defeat the purpose. again, for the position map, you have to consult the position map on each axis. You have to know exactly which index to access. And if the attacker knows what index within the position map you access, the attacker knows which block you are getting from the server, from the ORAM trees. So again, that would defeat the whole purpose of ORAM. So to do this, we use cmove. Cmove is a x86 instruction which is called conditional move. So what cmove is going to do is that it is based on cmove uses a flag value. Based on the flag value, it is either going to, let's say you have A and B memory locations. So based on the flag value, it would either copy A to B or it would not. But even if it does or it does not, it would exhibit the exact same memory patterns because it would access A and then access B in this exact format. But what it would just do is that it would ensure that whatever the flag value is, it would either copy it from A to B or it would not. But again, it would exhibit the same memory traces so the attacker, so any attacker that is simply looking at memory traces cannot really figure out what's going on. So using cmove, we're going to technically access each index in the position map and each index in the stash, and at the end of it, what the attacker sees is that all of them were accessed. The attacker doesn't really know which one exactly it was. This is, I admit, an expensive operation, but this is required because unless you're able to completely protect the stash and the position map, there is no point of using ORAM, because then you would be creating a side channel in your ORAM implementation. So we're calling this a side channel resistant ORAM implementation. And next part is technically related to performance, is how we improve performance. So again, in the ORAM model, there is the client, there is the server. So the ORAM client is just the metadata information and a small memory region to hold memory blocks. So it is a small region, so it can technically be fit within the enclave without much problem because it's a very small region. If you remember, the enclave was just a 128 megabyte region. So the enclave does not have a lot of space. The enclave does support paging, but again, I would explain why that's not a good idea. So the metadata information, which is small and can be easily fit within 128 megabytes, you can just keep them within the enclave. But whereas the ORAM trees have to be kept outside the enclave in an encrypted manner because they're extremely large, and they're going to be more than a few gigabytes in memory, in memory space. So, okay, just to give you an illustration why this is required. So if you can see, the EPC region is a small memory region, whereas the program might. So as regular programs, if you remember that regular programs have, let's say you have 16 gigabyte of DRAM, but your program might be using 32 gigabytes of space. So how does that happen is because you have swapping. You can swap pages in and out of the disk. So similarly, for SGX, although this is just a 128 megabyte space, an enclave can technically use more than 128 megabytes. It can use 64 gigabytes of space. How it does that is simply that it simply swaps in and out of the DRAM, very similar to how normal processes swap in and out of disk. The swapping in and out of DRAM is although much faster, but it is still very expensive, and there's a whole paper on it on how expensive enclave exits are due to swap in and swap out. So if we keep everything within the enclave, which we technically can, it would be extremely expensive and very, very and not really friendly to performance. So as a result, we use custom encryption and ensure that the ORAM trees are stored outside the enclave. So encrypted ORAM trees are stored outside the enclave for performance reasons. So leverage. So this is the last part of Obliviate, of the design of Obliviate. So suppose that we're going to another performance improvement that we thought about was to leverage asynchronicity. So what happens is, let's suppose you have a database application that is going to say, okay, I need to read this certain file at this certain offset, and it's going to send it to Obliviate, to our file system. What the file system, so within the file system, we use two threads. One thread is the front-end thread that handles all incoming requests. One thread is the back-end thread that handles all the file, whatever request that the application made. So the front-end thread is just going to say ask the back-end thread to read whatever block it is, and then the back-end thread is going to read it and going to reply right then. So we can just so by using this, we can ensure that we can ensure that write back is done by the backend thread, whereas the front end thread provides the reply to the user. So by doing this, we are technically saving log of n operations, log of n stoppage time, because while all file system calls are blocking, so that means that definitely the program is waiting for the request before it can resume operation. So yeah, we're going to perform asynchronous write back. So the implementation is using just the Intel SGX software development kit, which has already been provided by Intel. We use Graphene SGX, which is a library operating system, to run some heavyweight applications. You should just think that the library operating system is sort of like a very small operating system within the enclave that provides functionality to run heavy applications. So for performance evaluation, we took 3 reference file systems. One is the native file system, which is just a regular Linux file system. We use the in-memory file system that I explained at the start of this presentation, and we also use the Obliviate, our own file system. So we show ISON benchmarks, and we can show that while comparing Obliviate and the in-memory file system, their performances are actually very similar. So we have very little overhead, less than 3 times overhead. I won't say very little, but still less than 3 times overhead against the in-memory file system. The reason for that is that the in-memory file system, again, is extremely slow. If you keep everything within the enclave, then that is not really that's not really a good approach, because again, the enclave has very small physical memory, and in-memory file system exerts a lot of pressure on it. Well, when we're comparing very small file sizes, we are even comparable to the native file system. But again, when we go to larger file sizes, we lag behind by a degree, which is expected because the native file system is completely insecure. And well, so then we did some macro benchmarks using SQL Lite and Lite TPD. So for Lite TPD, we used a range of different file sizes, and we tried to access them, and we tried to insert and select 500 queries from SQL Lite. We show that even for macro benchmarks, Obliviate shows almost less than 2 times overhead over the in-memory file system. And again, the in-memory file system is also insecure, but it is the next best secure version of file systems that we have currently. And in conclusion, I would say that first of all, it's very risky to focus on mitigating a single side channel, as a lot of previous work has done. And Oblivious Ram can definitely be used to provide reasonable security. Of course, there are performance drawbacks and huge performance drawbacks, but Oblivious Ram can technically provide you very sound security and should definitely be considered as an alternative. Obliviate, in a nutshell, is that it provides a secure file system library for Intel SGX. Well, we use path ORAM to ensure that all file-related system calls are handled securely. We leverage cmove to secure the ORAM implementation, and we also talk about SGX-specific optimizations to ensure that we sort of provide a close enough performance to the next best insecure file system, which is the in-memory file system. And that is it for my presentation. Thank you so much for listening. If you guys have any questions, I'm happy to answer them.
So let's take our speaker first.
Thank you so much.
Any questions? Maybe I can force again. No.
Any random SGX question. I mean, it doesn't have to be focused on this. Anything that you might think about for SGX? Yes, please.
Our data is stored on the disk.
Do you mind if you could use that microphone? I'm sorry to mention. Are files stored on the disk encrypted, or they are just plain text?
Files stored in the disk?
Yeah.
So by the disk, you mean just give me
I mean,
disk,
yes,
right?
on the right.
So they don't technically need to be encrypted, right? Mm-hmm. But yeah, let's say they are encrypted, but they don't technically need to be, because as long as you ensure No, yeah, it would be better than they're encrypted, definitely better than they're encrypted.
Right.
Because otherwise, when you're going to dump everything back, then the attacker would still know what changed. So you
So-
definitely have to keep everything encrypted.
So if you keep everything encrypted,
Mm-hmm.
then why is it important to protect from the adversary knowing that which block you've accessed? Given
So-
the fact that everything
Okay,
is
so
encrypted.
one very simple way is to ensure that let's just read the whole file. Okay, that's the first thing that comes into mind.
Mm.
Okay, if we read the whole file, then it is definitely completely secure. Yes, but let's suppose that your encryption is done block by block, which is generally the encryption that is used. So you're going to use a block by block encryption to ensure that means that you don't have to read the whole file. If you want to read the whole file, that would be secure, but that would be even more performance hazardous than ORAM.
No, actually, my question
Yeah.
is, if the file data itself is encrypted,
Yes.
why is it important to protect from the adversary
Right.
knowing which block you've accessed?
Right. That's a good question. So again, if you remember the attack that I illustrated at the start, it doesn't really matter what the data is. What matters is that it's sometimes, even if the attacker doesn't know what data is, he can somehow sort of leverage any sort of small information to figure out what is being run. So in this scenario, let's say the attacker knows what the database semantic is. If the attacker knows what the database semantic is, it doesn't matter if he knows which query it is, because he can still say, okay, this guy, this IP address gave me this query and tried to access this index within the SQLite database. So the attacker, let's say that later on that data is perhaps public or something, made public or something, then again, the attacker has some information that it can use to leverage. Similarly, there have been other attacks that have used side channels to break whole RSA crypto keys using, again, database side channels such as page tables and cache-based attacks. So there are multiple versions of why we need to secure against these side channels, but especially for file systems, this is one guiding example of why you might need it.
Actually, I have one more question.
Yes, please, right.
Can you go to the slide where you show the, I believe, the ORAM trees?
Yes.
And where you mentioned randomizing
This?
block, yeah,
Yes.
randomizing write back.
Right.
So if you try to write back a block back into the tree, the adversary will be able to know where you've write back to, right?
Right, but maybe I wasn't very clear, but you don't write back one block, you write back the whole path. So you're going to write back this path, this root node, and then you're going to write back this node here also, and then this node here also.
Yeah, we can't see what you're
We can't see where you're pointing at.
I'm sorry. So what technically is going to happen is that you are, let me just show it from here. So you are going to write back here, 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 and here, the whole path, instead of just a single node. So if you just write back here, then the attacker already knows where you've written back, and then the attacker knows where you wrote back the real block, definitely. But since you're going to write back to the whole path, the attacker still doesn't know exactly where it could be. It could be here, it could be here again, right? It could be the same space, same spot. It could be here, it could be here. The attacker doesn't know. So the whole point is that since the attacker doesn't know, it cannot correlate the next time you're going to try to access it. So if the next time you try to access this path again, the attacker could think that maybe it's the same block, maybe it's a different block. The attacker doesn't know because he couldn't correlate from your first access.
So the first step is just trying to erase the trace, right?
Right.
It's similar to erasing a trace, but you have to put block A back to somewhere,
Yes.
like in the 1,
Yes.
0.
Yes, yes.
Like the left subtree of the right subtree. Right.
Yes.
So your program will try to write to that position.
But our program will try to write through all different positions. So these are dummy blocks, but these
Yeah.
are also blocks that you're trying to write, and these are going to be encrypted. So since everything is encrypted, you're also going to write here. You're also going to write here. So the whole point is, since you're going to write to the whole path, to every node in the path, you're not just going to write here. Now this is a completely trusted memory region. The attacker doesn't know what's going on there. The attacker only knows that you gave it some memory to write here, and then you gave it some other memory to write here, and then you gave it some other memory to write here. The attacker knows this much.
I believe there's another phase of the write back, right? Because you have to position A into the new randomized
Right,
position.
but you're just going to give that information to the attacker. You're going you can sort of create that, right? You can start from here, start writing back
But-
whatever you can here.
This is pretty complex problem than you may think. And the key idea is that if you are simply writing the single block, then the attacker will know, right?
Yes.
So instead, maybe you can simply write the whole node that is another direction, but that's going to be too slow, right? Attacker will have no idea which block has been written because if you are simply newly updating entire blocks, that's going to be too slow. So this is smart trick, having the sort of the tree, the organization, and
So-
only updating the path. And now you can
I
prove
see.
this is somehow as secure as entirely updating the block.
So
all the
we
blocks.
so we need to write back to a lot of dummy nodes, basically.
But it is trying to minimize those the extra dummy nodes.
Because this is still a log of n
So
rather than n.
in a real world tree, how deep are the branches?
So it depends on your data, right? So in the path ORAM construction, what they say is as long as the number of real blocks in your tree are equal to the leaf of your tree, you can provide guaranteed security, the same as random,
okay, I
completely
see.
random.
So by the way, this is very smart trick that is done by our Purdue graduate.
Okay.
Yeah.
So I kind of wanted to know, say that I'm somebody who is actually planning on using this and I'm signing up for, say, some sort of database hosted on a cloud service. It seems like from my perspective, I'm just, making queries, getting responses.
Right.
What is stopping an adversarial server from essentially lying to me and pretending they're running all of this rather than actually doing it?
So pretending from running all of this,
They
that
could
is why-
hide it, couldn't they? Essentially, is there any way that you could get around that perhaps and be sure that this is what is being done?
So there is a sort of remote attestation that is possible with SGX, where you can sort of say that, okay, we're using another enclave, you can sort of attest that whatever is being run within this enclave. Now, there is still no guarantee that they're actually going to run it within that enclave and give you data, but as long as you ensure that remote attestation that you do with that enclave and your enclave, they match, because you have to also involve Intel. Intel is the one that can sort of give you the go ahead that, okay, yes, whatever this attested, let's say, MAC was given to you is from another enclave. So you can sort of say that this is secure.
So do you have any more questions?
Any other questions?
If not, let's thank our speaker again.
Thanks a lot, guys.